Hello students, welcome back to JCE Connect. So in previous lecture we have derived the equation that is a jet striking a moving curved vane tangentially at one of the tips and leaving at the other, and that case was an unsymmetrical case, and we have solved that case by considering the velocity triangle, and we have drawn velocity triangle at inlet and outlet, and finally we have calculated the force exerting by the jet on the vane in the direction of jet as well as the work done by the jet considering single vane. So in this particular session I'll be taking some numerical problems on velocity triangle, how the problems can be solved by using a velocity triangle. Let us see that take a first example. A jet of water having a velocity of 20 meter per second strikes a curved vane which is moving with a velocity of 10 meter per second. The jet makes an angle of 20 degree with the direction of motion of vane at inlet and leaves at an angle of 130 degree to the direction of motion of vane at outlet. Calculate the first one, the vane angles, so that the water enters and leaves the vane without any shock. Then work done per second per unit weight of water. Work done per second per unit weight of water striking the vane per second. So this is the problem given here. So we need to solve this problem by drawing the velocity triangle at inlet as well as at outlet. So first let us draw the velocity triangle. So here the vane, this is the vane given, curved vane. So first you draw the velocity triangle. Let us consider here the nozzle is been fitted like this. Here the nozzle is fitted. This is the nozzle. Then from this nozzle the jet is striking the vane like this. Then this is what, this is velocity v1. Then when the jet strike the vane starts moving in this direction, x direction u. The velocity of vane will be the u. Then that is represented here. This is represented u. Then join this one. This is VR1. And the absolute, this V1 is absolute velocity which is making an angle of alpha. This is called nozzle angle or the guide blade angle. Then you resolve the V1, when you get horizontal component, then that will be what? VW1, and this will be making an angle of theta, and this will be what? VF1, that is a flow velocity, that is nothing but V1 sine alpha, and this will be V1 cos alpha, and this up to here, this is U1 and this is VR1 cos theta. Okay, this we know how to construct the velocity triangle at inlet. Similarly, in this case, what are the data given here? I'll write a given data here. I'll write a given data. What are the data given here? The absolute velocity, that is v1, is given 20 meter per second. Then velocity of vane is given, that is u1 at inlet, that is 10 meter per second. Then angle made by the jet at inlet with the direction of motion of vane, that is alpha, is given, that is 20 degree. Angle made by the jet with the direction of motion of vane. Then also the angle made by the leaving jet with the direction of motion of vane, that is also given. So angle made by the jet, angle made by the leaving jet with horizontal is given as 130 degree. Okay, means here the jet will be striking. So when the jet strikes, see, this is the vane. This is the vane, and vane is moving here after striking. Then this will be drawn like this. This is V1. Okay. Then this will be, this is VR2, this is U2, then this one is V2, and this is a horizontal, and this angle is given, that is 130 degree. So this is U2, this will be V2. Okay, then this is perpendicular. So this, let us mark here, this one is E, G and H, this will be F, and this component is VW2 as we know, and this angle is beta. This angle is beta. So this is angle 130 degree, and then if I draw this one, if this also, what is this? This total angle is 180. 180 minus 130, this angle what we get, 50 degree. Okay, this whole angle, but this angle is pi. This angle is pi, this is theta. Okay, so now we need to calculate the vane angles at inlet and outlet, that is theta and pi we need to calculate here. So the jet is leaving by making an angle of 130 degree. So this is the leaving jet. The jet is leaving the vane at outlet by making an angle of 130 degree. That is angle between that is V2 and horizontal, that is given. Okay, so remember this one, and this will be what? VF2. VF2, and this one is, if you take this one, this angle, that angle is beta minus pi, and this angle is pi. This one, only this much, angle between VR2 and horizontal pi, and angle between that is V2 and horizontal this side, that is 50 degree, because 180 minus 130 is 50 degree. So just to construct outlet velocity triangle as well as inlet velocity triangle, so once you construct, then you can easily calculate here. Now here I can write beta will be 180 minus 130 is equal to 50 degree. So in this problem here U1 equal to U2 equal to U equal to 10 meter per second, and also VR1 is equal to VR2, because when that is the blade passage has been assuming very smooth, there is no losses at all, because it is given in a problem, so that the water enters and leaves the vane without any shock, without any disturbance. Okay, so it is be very smooth. Then U1 equal to U2 equal to U equal to 10 meter per second, VR1 is equal to VR2. Now we have to calculate by referring this velocity triangle. We have to calculate vane angles at inlet, means at what angle the jet is entering into the blade passage, that is theta, and at what angle it will be leaving, so at inlet as well as outlet. Okay, so this is the angle of that is the jet leaves at an angle of 130 degree, leaves at an angle of 130 degree to the direction of motion of vane at outlet, means they have to take angle between V2 and 130 degree. Okay, this is angle of deflection. Actually this is angle of deflection. Then vane angle, so this one Vane angle, that is a pi, you have to calculate. Now next, so now first part is Vane angles at inlet and outlet. Okay, now angle made by the relative velocities at inlet and outlet, that is theta and pi. Now from figure, that is from inlet velocity triangle, so triangle BCD, if you refer triangle BCD, in triangle BCD, if you are referring triangle BCD, look at this figure. So let us mark this point as a A, this is B, and this one is C, and this is D. A, B, C, D. If you refer this triangle BCD, this triangle is 90 degree. If the triangle is 90 degree, we can easily apply the trigonometric function and get the values. Okay, so in triangle BCD, so what is tan theta? So in triangle BCD, what is tan theta? Opposite by adjacent, BD by CD. So in triangle BCD, tan theta equal to BD by CD. But what is BD? Just to refer again this triangle, what is BD? So BD is what here? VF1. VF1 is nothing but what? V1 sine alpha, and CD is what? VR1 cos theta. So write that one. BD is VF1 and CD will be VW1 minus U1. So look at this figure. So actually CD is what? VR1 cos theta, that is nothing but VW1 minus U1. Then what is VF1? VF1, but VF1 is what? V1 sine alpha, and V1 is given and sine alpha is also given, so you will get 6.84 meter per second velocity. Similarly, what is VW1? VW1 is sine V1 cos alpha, then you will get 20 cos of 20, you will get 18.79 meter per second, and also U1 equal to what? 10 meter per second, that is given. Then next, tan theta equal to, substitute in the above here, substitute, you will get 6.84 divided by 18.79 minus 10, you will get 0.778. Then from this, what is theta? Calculate your theta. So theta will be 37.875 degree. This is inlet Vane angle. Also from, once again, from inlet velocity triangle, that is refer triangle BCD, what is sine theta? Refer sine theta, that is VF1 sine theta, opposite by hypotenuse, VF1 divided by VR1, opposite by hypotenuse, it is BD by CB, BD by CB, then that is VF1 divided by VR1. So we need to calculate VR2 with, then VR1 is what? VR1 will be VF1 divided by sine theta. VF1 already calculated 6.84 sine of 37.875. Then you will be getting 11.14 meter per second. Therefore, VR1 is equal to VR2 is equal to 11.14 meter per second. Then again refer, that is triangle, can refer this triangle here, refer triangle. So again from triangle EFG, so you refer outlet velocity triangle EFG, this triangle EFG. Since it is not a right angle triangle, so you have to apply here either sine rule or cosine rule here. So applying sine rule. So you know the sine rule. If suppose this is a triangle, if the sides are say A, B, C, and it is, this angle is a small c, this is a, and this is small b, then notice what the sine rule says. The A divided by sine A is equal to B divided by sine B is equal to C divided by sine C. This is the sine rule. So for this triangle EFG, you apply the sine rule. So when you apply the sine rule, VR2, this one VR2, because we know this angle, okay, this opposite angle we know because this is 50 degree. So to apply sine rule, you should know the inner angles. Okay, VR2 divided by sine of 180 minus beta, this one, this angle is sine of 180 minus beta is equal to U2 equal to, because we know that two sides, U2 equal to sine of this angle beta minus pi. Okay, so when we know the two sides and also the angle, the other can be calculated easily. So here substitute 11.14 divided by sine of 180 minus 50, because we know the value of beta and also we know the value of U2. Then sine of beta also we know, but unknown is what? Pi. Then calculate this one, simplify. So 14.542 is equal to 10 divided by sine of 50 minus pi. Then sine of 50 minus pi is equal to what? 0.6876. Then you will be getting 50 minus pi, you will be getting sine inverse of 0.6876. Then 50 minus pi, you will get 43.44. Then pi, you will get 6.56 degree. So these are the inlet and outlet. So inlet angle also you got. So inlet angle 37. Look here. So this is the inlet Vane angle and this is the outlet Vane angle. Okay. So finally you have to get the outlet Vane angle. So here we have applied the sine rule since we know the two sides and also inner angles. You know how to apply the sine rule and all. You have learnt in mechanics. So apply the sine rule here. Then second part is what here? You have to calculate work done per second, but per unit weight. You have to calculate per unit weight. So we know Fx formula. Fx formula is what? Rho A VR1 VW1 plus or minus VW2. This is the formula we are knowing. But since beta is less than 90 degree here, so beta is less than 90 degree, the formula you have to use rho A VR1 VW1 plus VW2. This is the formula. And work done per second, the formula is Fx into velocity, that is velocity of plate. Then we know Fx is rho A VR1 into VW1 plus VW2 into U, and this will be force, that is work done per second, but we want work done per second per unit weight. So per unit weight, how to calculate per unit weight? That is work done per second per unit weight. So that is rho A VR1 VW1 plus VW2 divided by weight per second, per unit weight per second. This is your divided by per unit weight. But we know the formula, weight equal to what? M into G. But we want weight per second, then we get weight per second, that is mass per second also you have to take here into G. But mass per second is, we know, V rho A VR1 into G. This is mass per second, mass flow rate, rho A VR1 into G. So this gives you weight per second. Then divided here, rho A VR1 VW1 plus VW2 divided by rho A VR1 into G. This get cancelled. Once we get 1 by G VW1 plus VW2. So this gives you weight, work done per second per unit weight of fluid striking the vane. Per unit weight of fluid striking the vane. Let us understand here, weight equal to M into G, but weight per second we want weight per second, anything, but again you have to divide it by time, then mass per second is what? Rho A VR1, that is mass flow rate into G. Then here this get cancels, finally you get this equation, then where VW1 is 18.794 meter per second, then VW2 from figure, so if you refer the figure VW2, refer this figure, so VW2 you will be getting GH, means GH minus GF, GH VW2 GH minus GF. Okay, so I'll write here GH minus GF. Then what we get here? VR2 cos pi minus U2. So look at this figure. So this one, this is total VR2 cos pi, this total. So VR2 cos pi minus U2 is VW2. Okay. Then substitute the values here. VR2 already we know 11.14 into cos of 6.56 minus 10. You will get 1.067 meter per second. Also U1 equal to U2 equal to 10 meter per second. Then work done per second, calculate work done per second per unit weight of fluid striking, 1 divided by 9.81, 18.794 plus 1.067 into 10. The answer you get 20.24 Newton meter. Okay, Newton meter per Newton. Newton meter per Newton. Okay, per Newton means per unit weight of fluid striking. So this is the answer. Okay, so here in this type of problems the very important thing is drawing of velocity triangles. So once you draw this velocity triangle, then it is very easy to calculate the things, components. Okay, this is the inlet velocity triangle and this is the outlet velocity triangle. Try to understand how to construct a velocity triangle at inlet as well as outlet. This is a standard form. So you have to construct like this, then you have to apply the trigonometric function, sine rule, cosine rule. Trigonometric function can be applied if the angle is triangle is 90-degree triangle, you can easily apply. And if you want to apply the what you call a sine rule or a cosine rule, so you know by using a trigonometry, the two unknowns can be easily determined from the data listed on the triangle. If the triangle does not contain a 90-degree angle, then the law of sine or cosine rules may be used for the solution. Okay, so I hope you understood this one. Please practice this type of a problem. So very important is how the jet is leaving, means at what angle the beta is at what angle at outlet the jet is leaving. So that is very important. You have to find out the beta. Based on the beta we have discussed in derivation, if the beta is 90 degree, if the beta is less than 90 degree, if the beta is more than 90 degree, how the force can be calculated. Okay, I think you understood this one. Similarly, practice other type of problems also. So we'll continue with one more problem on a velocity triangle. So that is a numerical problem on velocity triangle. So here the problem given as this problem. So let us take this problem. A jet of water having a velocity of 40 meters per second strikes a curved vane which is moving with a velocity of 20 meters per second. The jet makes an angle of 30 degree with the direction of motion of vane at inlet and leaves at an angle of 90 degree to the direction of motion of vane. At outlet, draw the velocity triangles at inlet and outlet and determine the vane angles at inlet and outlet so that the water enters and leaves the vane without any shock. So this is the problem given here. So first write the given data. The velocity of jet is given 40 meters per second, velocity of vane at inlet is 20 meters per second, angle made by the jet at inlet is alpha is 30 degree, then angle made by leaving jet is 90 degree. Okay, so with this, so angle made by the leaving jet at 90 degree, so the beta is 90 degree here. So next draw the velocity triangles. So let us draw this first velocity of jet, then the vane is moving in this direction u, then that you shift and keep here, then this will be u1, this shows the direction of vane, this is the jet direction, then the difference of these two will be the relative velocity vr1, then the component of v1 will be vw1, that is velocity of whirl and velocity of flow. So these are the two components of v1. So this will be v1 cos alpha and this will be v1 sin alpha. Okay, then the relative velocity will be making an angle of theta. This theta is nothing but vane angle at inlet, this equal to this. Okay, then triangle ABD represents the inlet velocity triangle. Okay, and this alpha is the guide blade angle or angle made by the v1 with the direction of motion of vane. Okay, so this is the inlet velocity triangle. First you need to construct this velocity triangle. After that, as the jet enters the vane passage like this and glides over the surface, and it is leaving by making an angle of 90 degree. It has been given in a problem. So here given, see, look at the way that jet leaves at an angle of 90 degree, at an angle of 90 degree. Okay, so in this one, so here this is the vane and the jet is leaving by making an angle of 90 degree. Okay, so if it is, this is 90 degree, then this beta becomes 90 degree. Okay, so when beta becomes 90 degree, the vf2 is equal to v2. Then the whirl velocity here, the vw2 will be 0. The whirl velocity at outlet will be 0. Okay, then this represents the direction of vane motion. This is u2, then this is the vr2, then this triangle EFG is a 90-degree triangle, that is right angle triangle, and this angle is pi, this also pi. Okay, then once we construct the inlet and as well as outlet velocity triangle is depending upon how the jet is leaving the vane, whether by making an angle of 90 degree or less than 90 degree or more than 90 degree, that you have to identify first. Based on that, you have to draw the outlet velocity triangle. In this case, the jet is leaving by making an angle of 90 degree. Hence, beta is also become 90 degree. So here, the beta angle is 90 degree. Then, for this problem, u1 is equal to u2 equal to u, that is 20 meter per second. The vane angles at inlet and outlets are theta and pi respectively. Then from triangle BCD, this is from inlet velocity triangle BCD. BCD, so apply tan theta equal to BD by CD, then VF1 by VW1 minus U1. So what is VW1? VW1 is nothing but the component of V1, that is V1 cos alpha, and V1 is given, alpha is given, substitute and get the value, that is, this is called whirl velocity at inlet. Then VF1, V1 sin alpha, that is a component, that is a vertical component of V1 sin alpha, then that 20 meter per second we get. Then U1 is given, then also tan theta is equal to 20 by 34.64 minus 20, it gives 1.366. So in the theta you get, this is theta 53.79 degree. Okay, then further this is the inlet velocity triangle. Then calculate outlet velocity triangle. Here from triangle BCD, once again the refer inlet velocity triangle. Sin theta is VF1 by VR1, then VR1 you will get 24.78, but VR1 is equal to VR2 because the passage of blade is assumed very smooth, there is no frictional loss, hence VR1 is equal to VR2. Then this one, then refer outlet velocity triangle EFG, this one. So refer outlet velocity triangle EFG, this one, EFG, refer this one. Then from the outlet velocity triangle cos pi u2 by VR2, because VR2 we know, we don't know the cos, what is the angle, so from this we get outlet vane angle. So this is the way outlet vane angle. Okay, this is one simple problem. So let us take one more example here. A jet of water having a velocity of 45 meter per second impinges without shock in a series of vanes moving at 15 meter per second. The direction of motion of vane is inclined at an angle of 20 degree to that of jet. The relative velocity at outlet is 0.9 of that at inlet, and absolute velocity of water at exit is to be normal to the motion of vane. Find the vane angles at inlet and outlet. Work done on vanes per Newton of water supplied by the jet and hydraulic efficiency. So here first try to understand the problem and also what are the data given here. So here the data is given here. Velocity of the jet is given, means from the nozzle the jet is coming with the velocity of V1 45 meter per second, and velocity of vane, once the jet hits the vane like this, the vane here, the nozzle is been fitted like this. So from this nozzle the jet is coming out and it is striking the vane. Okay, so V1 is given absolute velocity before striking the vane 45 meter per second. So when it strikes the vane starts moving, that is the vane velocity u is given, that is u1 equal to u2 equal to 15 meter per second, and angle made by the jet at inlet with the direction of motion of vane, means this one, this angle made by the jet with the direction of motion of vane, that is alpha is also given. that is 20 degree. Then the relative velocity at outlet. In this case, the relative velocity at outlet means whatever velocity with which the jet is striking at inlet, that is VR1, but when it glides over the surface because of the some losses. So at outlet, the relative velocity is only 90% of inlet relative velocity. We are getting only 90% here. Hence, VR2 is 0.9 VR1. It is given in a problem. Then Vane angles at inlet and outlet. Vane angles at inlet and outlet are theta and pi as usual. Then you have to construct the velocity triangle first. So draw V1, draw U1, then VR1. Join this one, and alpha is the angle made by V1 and theta is the angle made by VR1. Then VW1 will be the component of V1 in horizontal direction, and VF1 is a component of V1 in vertical direction. VW1 is a whirl velocity, VF1 is a flow velocity, then theta is the vane angle at inlet. Similarly, at outlet, the jet is leaving the vane by making an angle of 90 degree, that is V2 equal to VF2. Hence VW2, that is whirl velocity, will be 0 here. So in this case, because the jet is leaving the vane by making an angle of 90 degree, hence beta is also 90 degree. Then this is the vane velocity. Vane velocity is at inlet tip as well as outlet tip. Both are moving at same velocities. U1 equal to U2 equal to 15 meter per second. And this is pi. This is also pi. Then let us name the triangle EHG. Okay. So once you draw the velocity triangle at inlet and outlet, then you can easily calculate the vane angles at inlet and outlet. Just to apply the trigonometric function, that is in triangle BCD at inlet velocity triangle, tan theta equal to BD by CD. Just refer the triangle BD by CD. BD by CD, VF1 divided by AD minus AC, then VF1 divided by VW1 minus U1. So this is VW1 minus U1, you will get this one. Then where VF1 is equal to V1 sin alpha, 15.39 meter per second. Similarly, calculate VW1, V1 cos alpha, then 45 cos 20, then 42.29 meter per second. Then tan theta is 50, calculate tan theta, substitute here and you will get this one. Then theta you will get 29.42 degree, that is inlet vane angle. Again from triangle BCD, once again you calculate from the BCD. So we need to calculate what is VR1. So once we get to VR1, then we can easily get the VR2 at outlet. So with that intention, you have to refer again triangle BCD, apply sin theta VF1 by VR1, then calculate VR1. VR1 is VF1 by sin theta. Then get sin theta VR1. This much is the VR1, but at outlet VR2 will be 90% of VR1. You will get 28.2 meter per second. Then refer outlet velocity triangle EGH. We have cos pi equal to U2 by VR2. Then 15 divided by 28.2, you get this much. Then cos pi. Then you will get the vane angle at outlet, 57.87 degree. And they asked also work done on vanes per Newton of water, that means per weight. So work done per second per Newton of water striking. This is the formula. So we know that is 1 by G into bracket VW1 U1 plus VW2 U2. This is the formula we are having. But U1 equal to U2 and also whirl velocity at outlet will be 0. Because the jet is leaving by making an angle of 90 degree, the whirl becomes 0 there, and U1 equal to U2 equal to U. Then finally we get 1 by G VW1 into U. Then substitute here, you will be getting 64.66 Newton meter per Newton second, or joule per second by per Newton. This is a work done per second. Then efficiency is what? Output by input. Output is work done per second, and input is kinetic energy per second. And output, we know the formula output, VW1 plus VW2 into U, then divided by input is V1 square by 2G. And this V1 square by 2G, this is for a series of vanes. So this, whatever the equation we have taken, this is for series of vanes. Because so look at this Efficiency is work done per unit weight, then kinetic energy per unit weight. So work done, how we write? Fx into u. Then this will be v1 square by 2g. Okay, so v1 square by 2g. This is per unit weight. Weight is what? Weight can be written as m into g. Okay, then m into g, this will be what? Weight per second. Again per second, what we write here? Rho a v square into g. Rho a v square into g. But kinetic energy per unit weight. Kinetic energy per second per unit weight. When you write half mv square, but per unit weight. So when you take a per unit weight, you divide this one, you will be getting this one. Okay, kinetic energy per unit weight, this divided by this one. Okay, so again mass per second. So means when you take kinetic energy per second, that is rho a v cube, we get kinetic energy per second divided by this one per unit weight, rho a v square into g, but half. This get cancels, one velocity get cancels, sorry, half mv square will get. So once we get this one, we get half v square by g. Okay, so we get that one here, v square by 2g for a series of vanes. Substitute here, you get the efficiency. So this is a simple problems. So please solve this kind of problems, and very simple. Only you have to remember how the jet is leaving the vane. So refer any textbooks. So solve the problems given in the textbook. Practice solved problems only. You will understand in a better way. We will continue with some more problems on impact of jet on curved vanes, considering the velocity triangle. So in this particular session, I will be taking a problem as a jet of 60 mm diameter impinges on a curved vane and is deflected through an angle of 165 degree. The vane moves in the same direction as that of jet with a velocity of 25 meter per second. If the rate of flow is 190 lps, determine the component of force on the vane in the direction of motion. The next, how much would be the power developed by the vane and what would be the water efficiency? Neglect friction. So this is the problem given, and first you need to write the given data. What are the data given here? The diameter of the jet is given 60 millimeter, so 0.06 meter, and the area of jet can be calculated. Then that is pi by 4d square. Then angle of deflection is given, that is 165 degree. Then the velocity of vane both at inlet and at the outlet, that is u1 equal to u2 equal to 25 meter per second. The rate of flow is also given, that is a discharge, q is 190 lps, that is 0.19 meter cube per second. So in this problem, they are not mentioned at what angle the jet is striking the vane. Since the jet and vanes are moving in the same direction, so let us take the jet is entering tangentially into the blade passage. So let us draw the velocity triangle. See, this is the vane, this is the curved vane, like this. Let us take at inlet, the jet is entering tangentially into the blade passage. Since it is entering tangentially, and also the angle made by the jet at the inlet will be 0. So here we need to consider alpha equal to 0 and theta equal to 0. Both are 0 here. So the velocity triangle will become here a straight line. So at the inlet, since they are not mentioned at what angle the jet is entering. So if they are not mentioned, you have to take the velocity triangle at inlet of this particular problem will be a straight line. Now, so you can mark on this straight line only. So let us take this point as a and this as a B, and this you mark as a C here. So A to C represent U1, velocity of Vane. Then this will be what? VR1. Then from here, velocity, that is from here to here, will be V1. So in this one, inlet velocity triangle, V1 will be equal to VW1. And in this problem, the velocity of whirl will be 0. Since the inlet velocity triangle is a straight line, it is giving a straight line, so we can mark only the velocity of the vane, because vane is moving in this direction, and the total velocity, the absolute velocity will be V1. So it is V1 equal to VW1, and VR1 is the relative velocity, that is V1 minus U1, which can be represented as CB, the line of CB. Then after striking the jet, so jet is striking like this, then after striking this, it exits like this. Then you can mark like this. Then this will be V2, and this will be, this is U2, and this is VW2, and this one VR2, and this angle is beta. Then this angle is pi. Then this will be VF2, the angle of deflection. You can take angle of deflection here. This angle of deflection is given 165 degree. Then this angle will become 15 degree. So this is the angle of deflection. So this is the pi, and this angle equal to this angle. Okay. So this will become VR2, outlet velocity triangle. Okay. So after this, once you have drawn the velocity triangle at inlet and at outlet, so at inlet velocity, this is the inlet velocity triangle. See, inlet velocity triangle, this is outlet velocity triangle. Okay. So inlet velocity triangle will be straight line, where AC represents, that is velocity of vane, where CB represents relative velocity, and AB represents absolute velocity. Okay. Then in this particular triangle, that is inlet velocity triangle, V1 is equal to VW. You will get only whirl velocity, that is a component of V1 in X direction, but component of V1 in Y direction will be what? 0. So you will get 0, that is flow velocity will be 0. But as it enters the blade passage, and exits, so the moment it strikes the vane, it will deflects. The deflection angle is given 165 degree. Okay, so that is a angle between VR2 and horizontal. VR2 and horizontal. Take this angle equal to this angle. This is also pi, and actually this is also pi. This angle equal to this angle, and this angle equal to this angle. Solve this one. You can write one line here. Since the jet of water moves in the same direction as that of vane, therefore alpha equal to theta equal to 0, and also the inlet velocity triangle will be straight line. Okay, therefore V1 equal to Q by A, because we know Q equal to A into V, so V1 equal to Q by A. Then Q is 0.19 divided by 0.002827, we get 67.5. 67.198 meter per second. Also VR1 equal to what? V1 minus U1. So that is 67.198 minus 25. We get 42.198 meter per second. Then VW1 is equal to V1 is equal to 67.198 meter per second also. Then from outlet velocity triangle, referring outlet velocity triangle, the angle pi will be 180 minus 165, you get 15 degree. Since the vane is smooth, VR1 is equal to VR2 is equal to 42.196 meter per second. VR1 is equal to VR2 is equal to 42.196 meter. Therefore, from outlet velocity triangle, so this one, if you refer this outlet velocity triangle, so this is U2 and this is VW2, and this will be up to here. This is VR2 cos pi. Okay, VR2 cos pi. Then what VR2 cos pi can be written? So VR2 cos pi, so VW2 can be written. VW2 will be VR2 cos pi minus U2. Then you know VR2 42.196 into cos of 15 minus 25, then 15.76 meter per second. Okay, so once you get a VW2, then you can easily get the force exerted by the jet, on the vane in the direction of motion of vane. Then Fx can be written. Since in this problem you look at this one, so here beta, just look at the angle beta, so which is less than 90 degree. Here beta is less than 90 degree. So for acute angle we write rho a VR1 VW1 plus VW2. So you know all here, VW1 also we calculated, VW2 also we calculated, then area, then substitute all the values here. Density is 1000, area is 0.002827, then into 42.198, then into 67.198 plus 15.76. Okay, then answer you will get 9896.37 Newton. This is the force exerting by the jet on the vane. Then work done per second. So we know the formula Fx into U. Then 9896.37 into 25, you get 247409.26 Newton meter per second. Okay. Then power developed by the vane, so power will be, so you'll get 247409.26 divided by 1000, we'll get 247.409 kilowatt. Okay, then efficiency of the jet can be written work done per second divided by kinetic energy per second. So already we calculated work done per second, then only calculate kinetic energy per second, that is we know half rho a v cube, or you can write half rho q v square, because q equal to a into v. Then substitute here, you will be getting, that is half 1000 into 0.19 into 67.198 square. So you will be getting here, just calculate 1000 into 0.19 into 67.198 square divided by 2, you will be getting 428.97 into 10 raised to 3. 10 raised to 3 Newton meter per second. Newton meter per second. Then substitute here. So we know the work done per second, 247.409 into 10 raised to 3 divided by 428.97 into 10 raised to 3. You will be getting 47.409 divided by 428.97. You will be getting 57.67 percentage. This is the efficiency of the jet. Okay, I hope you understood here. So in this problem, the important thing here is, so when the entry angle, that is a jet entering the vane passage, if not given, you have to consider this as a 0. Alpha equal to 0 and theta equal to 0. Alpha is what? Nozzle angle, and theta is the angle made by relative velocity with horizontal, and when both will become 0. So in this case, as you know, the component of V1, so V1 is what? V1, that is a VW1, sorry, component of V1, you can write, so VW1 will be V1 sine alpha, and VF1 will be V1, sorry, this is cos alpha, this is sine alpha. Okay, then VW1 cos 0 is what? 1, then V1 is equal to VW1. Sine 0 is 0, then VF1 will become 0 here. Okay, so the inlet velocity triangle will be what? Straight line you get. Okay, then mark the vane velocity and the relative velocity and the absolute velocity in this inlet velocity triangle, and the outlet velocity triangle. As the jet strikes, it deflects by an angle of 165 degree. The deflection angle to be taken, that is angle made by the VR2. When you draw VR2 and project that tangent and join to the horizontal line, you will be getting this deflection angle. So total angle is 180 degree, 180 minus 165, you will get 15 degree, and that 15 degree is this one. Okay, then again you draw the VR2, then you will get a beta. Beta is less than 90 degree, hence the equation will be VW1 plus VW2. Okay, so the drawing of velocity triangle is very, very important here. Once you draw the velocity triangle, then it is very easy to calculate the force exerting by the jet on the vane, as well as the power developed by the jet and efficiency of the jet. I hope you understood this problem. So practice this kind of problems, and generally this type of problems should be asked in exam for 15 to 20 marks. Okay, sometimes. So 15 to 20 marks. Thank you.